Ni apa benda ni yang mana?
Assalamualaikum and good morning everyone. Okay, so today we are going to look at tutorial 8 regarding the Hurwitz criteria. I hope you still remember what we have learned before last week, before mid-semester break. So let's look at some of the questions from tutorial number 8. Okay, so question 1, determine the stability of the following systems using suitable Hurwitz criteria, assuming the system as an open loop with a transfer function G. Okay, so firstly, what is an open loop? Okay, so later on we will see more about open loop and closed loop configuration. But I think you have seen this back in lecture number 1, okay, in first week. So let's look again what is open loop with a transfer function GS. Okay, so an open loop system basically has an input RS and then a transfer function GS and then output CS. Okay, so open loop doesn't have any feedback. Okay, so the system, the block diagram will look like this. So GS basically relates the output with input, so you don't have to do block diagram simplification for this case. Okay, so you are given the transfer function GS, so you can straight away use the denominator to create the Hurwitz table. Okay, so let's look at question A. Okay, so for question A, let's take the denominator. And then from here, you can generate the Hurwitz table. Okay, so we start with S power 4 and S power 3. And then we fill in the two top rows with the coefficients alternatingly. And then you can calculate row S2 using the determinant formula. And then continue with row S1. And then row S0. Later on, you can check again. Maybe I make some mistake. So then you can determine the stability by looking at the first column. Okay, so on the first column, so you look here. So this is positive, 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 negative, positive. So you have one sign change here, and then another sign change here. So here we have two sign changes, meaning that there are two poles on right hand side of S-plane. So when you have poles on the right hand side of S-plane, meaning that the system is not stable. Okay. Okay, so kind of straightforward, but you have to be careful when calculating the determinant. Okay, so if you calculate it wrongly, then your answer will be wrong. Okay, so make sure you calculate the determinant and make sure that the values inside the determinants are correct. Okay, now let's look at question B. So firstly, we take the denominator. And then we generate the Routh table from the denominator here. So we start with s power 5, followed by s power 4. And then we calculate for row S3. Okay, so here we encounter a 0 in the first column. So when we encounter a 0 in the first column, then we need to do modification on the denominator. Okay, so we need to do modification. So there are two ways you can do this. Firstly, you can assume this 0 as a small number epsilon, and then you calculate as usual for the subsequent rows. Then you can assume the epsilon either a small positive number or small negative number, and then determine how many sign changes when you use positive small positive number and small negative number. Okay, but that way is quite maybe maybe involves a lot of calculation to some of you, but there is another way, which is by reversing the coefficient of the denominator. Okay, that's an alternative way to do this. So let's reverse the coefficient, which is a lot easier. Okay. Okay, so we reverse the coefficient. And then from here, we can generate the Routh table again. So we start with s power 5, followed by s power 4. Okay, calculate row S3. Okay, so now we don't have any zero in the first column, so you can continue as usual. Okay, so I stop here for this calculation because it will involve a lot of decimals. Okay, so maybe you can try later and see how can you determine the system stability looking at the first column. Tutorial 1C. Okay, so the denominator is okay. So now we can generate the table. To calculate S4 as usual. Okay, so then we calculate for row S3. So from row S3, if you calculate later, you will get all zero in the first in this row. Okay. Okay, so you can zero in this row. In an entire row, what we need to do is we need to generate a new polynomial. Okay, so how to generate a new polynomial? So to generate the new polynomial is by looking at the row above the zero rows. Okay, the zero row. So the row above is row S4. So we create new polynomial from row S4. So here 1 S power 4 plus -3 S squared plus -4 S naught. Okay, so you drop by power of 2 for each S. Okay, so we get S power 4 minus 3S squared minus 4. And then from here, you need to differentiate P with respect to S. So you get 4S cubed minus 6S. Then you use this as a replacement for row S3. Okay, so you replace row S3 with this. So continue again, S3. We'll use this value, okay, 4, 6 minus and 0 here. Then you calculate row S2 as usual using row S4 and S3. Okay, so ignore this row of 0 here. So we use row S4. So we have 1, 4, -3, -6 over 4. So we get and then here we have 1, 4, -4, 0. And then I leave it to you to calculate S1 and S0 and determine the stability of the system, okay? Because now it will have decimal numbers, okay? So later on you can calculate by yourself and maybe if you want to show me whether your calculation is correct or not, feel free to do so. All right, so that's basically tutorial 1. Okay, so if you have any question, just let me know, okay? So now let's look at tutorial question number 2. Okay, so question number 2, determine the range K for the following system to be stable. Okay, so there are two systems here. So let's look at system number 1 here. Okay, so here the system is in closed loop. Okay, closed loop meaning that it has a feedback loop here. Compared to question 1, the question already gave to you that the system is open loop. So you don't need to simplify the block diagram. But question number 2, the system given to you is in feedback, okay? Or there is a block diagram given to you. So what you need to do first is you need to simplify the block diagram. Okay, so let's look at the first block diagram here. So here, the arrangement is in feedback. Okay, so you can simplify this using the feedback formula. So you can find the closed loop transfer function. By using the feedback formula. Okay, so this is negative here. So you have to divide by 1 plus, okay. So h is 1. So the feedback transfer function is 1. So you just divide by this value. Okay, so you will end up with then from this transfer function, you need to take the denominator. Okay, so take this denominator. And then you need to expand this first before you can generate the route table. So you can expand. So you can do this one by one, okay? If you don't know how to expand all of them all together. So I don't know how to expand all of them together, so I expand one by one. Okay, so after you get the denominator in complete polynomial form without factorization, then you can generate the route table. Okay, so as usual, arrange the coefficient alternatingly. And then calculate S square, rho S square. And then calculate rho S1. And then rho S naught. Okay, so later on you can check whether my calculation is correct or not. Okay, so what I did is congak. Okay, so maybe I did it wrongly. Okay, so now we want to determine the range of K for stable system. So what you need to do is you need to look at the first row, the first column, and then make sure that all of the values in the first column are positive. Okay, so stable system meaning that the first column must have all positive values. Okay, so that there is no sign changes. Okay, so this is positive, this row is also positive. So this row must be bigger than 0, and this row also must be bigger than 0. So let's analyze the range for K. So here, if you look at row S0, then K must be bigger than 0 for a stable system. Okay, for this column to have all positive values. Okay, so K must be bigger than 0. Now let's look at row S1. So this value also must be bigger than 0. So now let's determine the value of K. Okay, so you will determine, you will get that K must be less than 80. Then from these two range of K, you combine them together. So for stability, K must be bigger than 0 and then less than 80. All right, now let's look at the second question for question number 2. Okay, so the second block diagram here, the arrangement is slightly different from the first one. Okay, so what you need to do is you need to simplify first. So here, if you look at the arrangement of the forward transfer function of this system, then you can see that these two block, the controller and the rubber actuator and load, are arranged in cascade. Okay, so first you need to multiply these two together, and then you can perform feedback, okay, feedback loop, or simplify the feedback loop. So from here you can find the closed loop transfer function. So we multiply this cascade. So this is negative, then you divide by 1 plus. Then from here, you simplify the transfer function. And then expand the denominator to get the denominator in complete polynomial form. So here you get okay. So after you expand, then you can generate the Routh table. Okay, now after you generate the Routh table, then you can analyze the system stability or find the range of K by looking at the first column. Looking at the first column and make sure that all of them are positive. Now let's look at row S2 first. So we get 5.6 plus K must be bigger than 0. So K must be bigger than negative 5.6. Let's look at S naught first. So on S naught, we have 45 plus 10K bigger than 0. So we get K bigger than 4.5 negative. And then lastly, we look at row S1. So row S1, you need to expand the determinant first. So expand this. Okay, so we get this. Then you can use quadratic formula to get the value of K. Okay, so you can use calculator. So to determine the range of K here, if you still remember at maths, okay, then you have to draw something like this. So the first point here is negative 5.4. Okay, 5.41. And then the second point is negative 0.37. Okay, so we want it to be positive, meaning that we take the top part here. So the range of K for this row S1 will be K less than negative 5.41 or K bigger than negative 0.37. Okay, the lagging scale 0.37. So now we have so many range of K. So we get K bigger than negative 5.6, K bigger than negative 4.5, and this K less than negative 5.4, or K bigger than negative 0.37. Okay, macam salah kira tapi
Doktor,
yep.
yang S1 tu kan, dia punya metrik tu saya pun confused. Dia positif ke negatif? Yang 45 plus 10K plus or tambah ataupun negatif? Kan?
Dia negatif sebab dia negatif, meaning that 45 plus 10K minus 12 plus 11K times 5.6 plus K. Tapi kita ada negatif kat luar ni.
Oh no. Doktor.
So dia jadi negatif. Okay. I think I make mistake here. Tapi tak apalah. Okay. Later on you guys check balik. Okay. So the idea is that we have 3 different range. So you need to combine all of them together. Okay. So I think I made mistake, but tak apa, nanti saya check balik. Okay. And then let you know on our Wednesday. But let's finish it. Okay. So here we have negative 5.6. Okay, kena buat garis nombor. You have to make a number line. So negative 5.4. 4.5. And then this is negative 0.37. So firstly, you need to draw a number line. So K bigger than negative 5.6. And K also bigger than negative 4.5. And then K less than negative 5.4 or K bigger than negative 0.37. And then you need to find the range of K that intersect all of the 3 lines together. Okay. So can highlight. Okay. So here, if you take K less than 5.6, then there will be only this line intersect. Satu line je. So range ni tak nak lah, not this range. If you take range in between negative 5.6 until negative 5.4, you will find only 2 lines, this one and this one, but not this line here. Okay, so this range also not the range of K. If in between negative 5.4 until negative 4.5, you only have this line. So again, not this range. And then from negative 4.5 until negative 0.37, you only have these 2 lines here. Dua garisan je. So again, this is not the range that we want. And if you take from negative 0.37 onwards, bigger than negative 0.37, then you have this line here, and also the third line. So tiga-tiga garisan intersected here. Then we know that this is the range that we want. Okay, so the range of K for stability is when K bigger than negative 0.37. Okay, so ni dia punya range of K for stable system. Okay, so that's it. Okay, any question that you want to ask? Later on you can check balik. Okay, mungkin I make mistake somewhere while expanding the denominator ke. What I show here is macam concept lah. Okay, the concept on how to determine the range. Okay, so basically if you have so many range, then you have to do number line. Okay, ni dah belajar dulu masa dekat sekolah. And then if you don't have so many range, then you can just combine them together to get a suitable range of K. To column and make sure there is no sign changes in the first column. If there is sign changes, then the system is not stable. And then before you can generate the table, the Routh table, you need to simplify the block diagram. If you are given block diagram, and if you are not given any block diagram, for example, if you have open loop system, you just use the transfer function given to you. Sometimes, maybe on Wednesday, we will look at some system. Sometimes they just put here closed loop system, but not giving you the block diagram. So you need to simplify it first, even though there is no block diagram given. Later on Wednesday, we will see that kind of example. Okay, so what I want you to do right now is to make sure you fully understand Hurwitz criteria, how to generate the table, how to determine the stability, because this Hurwitz criteria will be used from here onwards a lot of time. Okay, you will use this a lot of time, so make sure you know how to generate the table and how to determine the system stability. Okay, so if you have no question, then that's it for today's class. See you again on Wednesday, inshallah. Assalamualaikum.